Okay, let's look at homework 6A. In the first problem, I want to show that any multiple of 6 is an abundant number, as long as it's strictly bigger than 6. Now you can use the formula for the sigma function here if you like, but I think it's probably easy enough just to go back and find a bunch of divisors. So what are we looking at? We're just taking a number like 6n, typical multiple of 6, and just make a list of divisors. You might call obvious divisors like 2 or 3, etc. You have n as a divisor, 2n, etc. And just look at these obvious divisors and show that their sum exceeds twice the value of the number you're starting with. So abundant means that sigma of n is bigger than twice the value of the number. Number 2, find all square-free perfect numbers and prove that there are no others. Okay, so we've got, when we deal with perfect numbers, there's the case of even perfect numbers and odd perfect numbers. So suppose n is an even perfect number, square-free. Then we have the theorem of Euclid and Euler that characterizes precisely what n looks like, the 2 to the k plus 1 minus 1 type of theorem. And so just use that result. Use the Euclid-Euler theorem. And then the second case is n is odd, and it's square-free, so say it's p1, p2, up through pk, a product of distinct odd primes. And then being perfect, you've got sigma of n should be 2n, and just use the formula for the sigma function. So sigma of n, show that that is equal to this, and then n itself is just p1, p2, pk, and then show that this is impossible. All right, this is 2 times a bunch of odd numbers over here, and then just think about even and oddness on the left-hand side, and that should lead you to some type of contradiction. Number 3, the sum of the squares of positive integers relatively prime to n. So sigma x squared, x running from 1 to n, x and n are relatively prime. Okay, now where is this quantity right here coming from? That's the characteristic function that will equal plus 1 when the GCD of x and n is 1, and it'll equal 0 otherwise. So that's picking out precisely the values of x that are relatively prime to n. And so let's just interchange the order of summation. So d is a divisor of x and n, so ultimately d must be always running through a divisors of n. Mu depends on d, and then x is running from 1 to n, x squared, and then d is a divisor of x as well. Right, to say d is a divisor of the GCD, that's equivalent to saying it's a divisor of both x and n. Okay, so if d is a divisor of x, let's say x is dy. X goes from 1 to n, so y goes from 1 to n over d. And so sigma x squared becomes sigma d squared y squared. And now you're going to need this formula here, sum of y equaling 1 up to some value, let's say capital L for instance. And that formula you should have encountered at some point. 1/6 L, L plus 1, 2L plus 1. So you're going to need that formula. You'll also run into this type of quantity again, and you know what that equals. That's the quantity that's equal to 0 unless n equals 1. So 0 for n bigger than 1. You'll run into the Euler-Phi function sum, this one here, sigma mu of d over d, so that was phi of n over n. And then finally, you're going to encounter a sum like this. And that's a multiplicative function that you can evaluate by calling it, say, capital F of n, and find f of a prime power, etc., using the fact that it's multiplicative. And so that should lead you to this quantity right here when you evaluate this type of sum. Okay, so that's enough said there. Prove that for any positive integer n, phi of n plus sigma of n is greater than or equal to 2n. So we've already seen this formula for the Euler-Phi function. Where the product is over the distinct prime divisors of n. And now I want to obtain a similar type of expression for sigma of n, but not as an equality, as a lower bound. So sigma of n, now let's start with sigma of a prime power. It's the sum of the divisors of the prime power, so that's going to be greater than or equal to p to the e 1 plus 1 over p. Okay, right. And so sigma of n is greater than or equal to n product p divides n 1 plus 1 over p. Okay, so use this type of, you're going to have to prove these two inequalities here, but then use those and then add phi and sigma together. So you'll have a product over the divisors of n 1 minus 1 over p plus the product over the divisors of n prime divisors 1 plus 1 over p. So what's your goal then? Your goal is to prove this inequality up here. So we have to show this quantity is greater than or equal to 2 for all values of n. And that's just kind of an algebra problem you can think about and determine when equality holds. So you can ask yourself right here, when does equality hold at that point? Here and therefore at this point. Find a formula for sigma mu times tau and sigma mu times sigma. Okay, so we have a standard technique for doing these when you have a multiplicative function. Let's just look at part A. Part B is exactly the same. So note that since mu and tau are multiplicative, mu times tau is multiplicative. And then use a theorem that'll say sigma d divides n of f of d is multiplicative if f is multiplicative. And so then call this quantity f of n, just let f of n be the sum in question. So you're going to say, well, that's a multiplicative function, so I just have to evaluate it at prime powers. And so just evaluate f at a prime power, equals, etc., and then use the multiplicative property to find f of n then. p1 to the e1, pk to the ek equals the product of the f values over the different prime powers. And then part B is a standard result, standard technique as well. In number 6, there's a related theorem we proved that said if f and g are both multiplicative and capital F is this convoluted sum like this, or you're summing over the divisors of n, you have f of d, and then you evaluate g at the complementary divisor n over d. So if f and g are multiplicative, and capital F is like this, then what can we say about capital F? It's also multiplicative. Okay, so that's a theorem in the notes we've proven. So phi is multiplicative, up there. Tau is multiplicative. So we have exactly a function of this type. And so now all we need to do is evaluate it at a prime power. So again, you're going to formally just define capital F of n. So use the colon to say, let's define it to be this sum. And then just evaluate f of p to the e. And what should it come out to equal? And show it equals the sigma function evaluated at p to the e. And then since both of these are multiplicative and they agree in prime powers, they will agree for all values of n. Okay, number 7, capital omega is the number of prime factors of n counted with multiplicity. So 12 is 2 times 2 times 3, so capital omega would be 3. Lambda is -1 to the capital omega power, and we want to first show that lambda is totally multiplicative, and then show that this sum is +1 when n is a square and 0 otherwise. So we're coming up with a characteristic function for the set of squares. Alright, so what is there to do then? Lambda is totally multiplicative. So let's just write down what omega is. So if n is p1 to the e1, pk to the ek, then capital omega by definition is the number of prime factors. So that's just e1 plus e2 plus ek. Okay, so take any two numbers, don't worry about whether they're relatively prime, write down their prime factorizations. Remember, the trick is use the same set of primes here. It doesn't even matter if you use that trick. P1 to the F1, PK to the FK. You could allow zeros, and it's not going to affect this formula here if some of those exponents are zeros. And then just show that omega of AB is omega of A plus omega of B. And then show lambda of AB is lambda of A times lambda of B. So we're trying to show lambda is totally multiplicative. And then once you've done that, you're going to define capital F to be this sum. Since lambda is multiplicative, capital F is multiplicative, and all you need to do is now evaluate capital F at a prime power in order to get the formula for what capital F looks like. Number 8. Okay, sum x going from 1 to m, e to the 2 pi I kx over m, 0 or m. So make sure that we're looking at the same thing here. So in that expression, x is an integer, k is an integer, I is the imaginary unit. So that's what we're looking at right here. And so let's call gamma the e to the 2 pi I k over m. This is what type of complex number? It's an mth root of unity. E to the 2 pi I k over m. So it's on the unit circle with the argument being 2 pi times k over m. And this sum looks like what? When x is 1, that's gamma. When x is 2, that's gamma squared. Gamma cubed. Gamma to the mth power. What type of sum is that? Just a geometric sum. And you know how to evaluate a geometric sum, so just use the formula for evaluating a geometric sum and show that it comes out to be given by this. And then in part B, we've got this constraint that x is running from 1 to m, but it has to be relatively prime to m, e to the 2 pi I x over m. So let's turn it into a complete sum. And then I have to put in a characteristic function that plucks out when x is relatively prime to m. So d is going to run through the divisors of x and m of mu of d. So there's a quantity that will be 1 precisely when this GCD is equal to 1 and 0 otherwise. And then interchange the order of summation. This reminds us of an earlier problem. So d runs through divisors of m, mu of d. The difference is here we're summing over the exponential. So x is going from 1 to m. D divides x 2 pi I x over m. So again, you're going to say x is dy. Y runs from 1 m over d, and then this inner sum is exactly a sum that we see in part A. Use part A. So convert it to y and use part A, and you'll see that that sum is always 0, except for one case, and in that one case, you're going to come out to get mu of m. And finally, number 9, so little f sub n is a sequence of positive reals. Capital F is defined as a product over the little f's. And now I want to come up with a Möbius inversion that expresses little f in terms of capital F. The difference between this and the classical Möbius inversion is we're dealing with products here. And in the theorem we stated in the notes, we're just dealing with sums. Well, you know a way of converting products to sums, and that's why I chose to let these be positive reals here. All we need to do is use the natural logarithm. So I want to prove this inverse formula. So let's take this starting expression, apply the natural log to both sides. Like that. And look what we have on the right-hand side. Sum over the divisors of n of some quantity right here. So think of this as sigma d divides n of some function of d. And we're trying to invert this. And so over here we have some g of n. So that is being g of n. And this is like this. So apply the Möbius inversion, and you would get g of n is sigma d divides n, capital G of d times mu of n over d. Okay, so use the Möbius inversion, and now bring back everything, and eventually you're going to want to exponentiate. So this little g of n is really log of f sub n equals blah, blah, blah. And so f sub n itself, in the end, is going to be e raised to something. And that should pop out the formula. And I think that wraps it up.